Greetings. So welcome to today's class. So let's continue from where we left off. If you recall, we were looking at steady state cornering, right? So, and we were essentially looking at, the problem of having Vx to be constant and R also to be constant. And we essentially looked at the low angle, small angle approximation and looking at the relevant models and the subsequent analysis. In the previous class, we looked at the from a dynamic systems perspective, what happens under various operating conditions using the steady state model. So the main reason we did was it like I just wanted to convey to you that all these observations which are typically taught is hold true under those bunch of assumptions that we studied. Okay, so that's what we looked at in the previous class. So today let's go forward and look at testing of steady state handling characteristics. Okay, so typically when we want to perform experiments, let's say on a car, and we want to essentially figure out what are the different characteristics of the vehicle, and we want to also get information about its cornering response. We perform experiments, and the variables that are typically measured include the steering angle, the longitudinal speed, and let's say the lateral acceleration and so on. And so these are the variables that are typically measured. And what happens is that like we use the steady state model, right? So for the model that we derived for steady state cornering, which if we recall, can be written as the following. So for steady state cornering, delta was written as L by R divided by, plus KV times Ex squared divided by Rg. Okay, so this is what we have, right? So this is what we have as the equation, governing equation for the steady state cornering maneuver. So depending on this, let's see what are the typical maneuvers which we do and what are the corresponding characteristics that come about, right? So let's first consider a simple test where we essentially hold the radius of turn constant. Okay, so we essentially keep on going on a curve of constant radius, and then like we measure the other parameters. Okay, like the steering angle and the longitudinal speed. Please note that we have to do things at steady state. Okay, so I am keeping on repeating and emphasizing that aspect in this entire discussion. So R is kept as a constant. So when R is kept as a constant, we know that delta is equal to L by R plus KV Vx squared by Rg. And Vx squared by Rg is going to be Ay by G, right? As we know, at steady state, the lateral acceleration, as we have already figured out, Ay is going to be equal to Vx squared by R, right? So how did we get this? Ay at steady state, okay, is going to be equal to Vx squared by R. Okay, so that's what we have used, right? So if we look at this expression and we essentially plot a graph between delta and lateral acceleration, for various operating conditions tests that we do, we can immediately observe that if I take the derivative of the above, not the time derivative, the derivative of the above expression with respect to the lateral acceleration Ay by G, immediately we get Kv. Okay, so because L by R is anyway constant. So the idea is the following, right? So we do these tests and then we do these measurements. So what happens is that like if I have a plot between delta and lateral acceleration, if the slope of the curve is positive, then I know the vehicle is understeer. The slope of the curve is negative, I know that the vehicle is in a state of oversteer, right? If the slope of the curve is zero, I know that the vehicle is in a state of neutral steer. Why? Because of the fact that the slope of the curve, which is this given by this equation, is in fact the understeer gradient, right? So that's what we can observe from this particular expression. Okay, so that's what we are able to conclude, right? So that's one important aspect that we have figured out, right, from the constant radius test. What are other tests that could be done? One could essentially look at what is called as a constant speed test. So what is this constant speed test? The constant speed test, like Vx is held as a constant. Vx is held as a constant. And then like we essentially drive the vehicle on curves of different radii, and then like we essentially try to figure out what happens to the steering angle input that needs to be given. Okay. So now please note that, from the expression for lateral acceleration, 1 by r can be written as ay by vx squared. Okay. So how did I get this expression? Here, just using ay is vx squared by r. So 1 by r is going to be equal to ay by vx squared, right? Is it not? So that's what we are doing, right? So delta, we are just going to rewrite it in a certain form. This is going to be L by R plus KV times AY by G. Let's use AY by G. Okay. So that's going to be, I can rewrite this as L times AY by Vx square. Okay, so we are just substituting for 1 by R, right? So L times AY by Vx square plus KV times AY by G. And this could be simplified further, right? So we can essentially write it as LG divided by Vx square times AY by G plus KV times AY by G. Okay, so it will be shortly evident why we are writing in this way. Now, if I take the derivative of the steering angle with respect to the lateral acceleration. See, once again, when we do these tests under different, let's say, speeds, different turning radii and so on, but then we hold those values constant in each experiment. And then we get measurement of this delta and the lateral acceleration. And we essentially, if we differentiate this expression for delta versus with respect to lateral acceleration, we get the answer as LG plus divided by Vx square plus KV. Okay, so this is what we have. So the point is, like if we are able to get the slope of this curve, we can always get the understeer gradient because we know LG, L and G and Vx, right? So we just we can calculate KV once we get the slope of the curve between delta and AY by G when we are doing this constant speed test. Okay, so that is the outcome, from this particular derivation. All right. Okay, so this is the second test that we do. Okay, so then another test which can be done is the constant steering angle test. Okay, so we are seeing that, like in each class of tests, we are keeping some variable as constant. Okay, and then like we are looking at the other variables and trying to get an information about KV. See, what is ultimately the objective of this particular set of tests? Like we need to figure out the state of the vehicle in terms of understeer, neutral steer, or oversteer. Okay, so that is going to be our objective. So with that in mind, when we deal with the constant steering angle test, the value of delta is going to be constant. Okay, and what happens is that, we keep delta to be constant, and then like we will be looking at other variables, right? Other measurements, and then like see what happens. Okay, so we give a constant value of the steering angle. So now what's going to happen, as we already know, 1 by r is ay by bx square. So delta is going to be equal to L divided by R plus KV Vx squared divided by Rg. Okay, so this is what we have. All right. So now what will happen if we look at this particular expression? We see that, like the left-hand side is delta is constant. The right-hand side, let me write it as L times 1 by R. Okay, and plus KV times AY by G. Okay, so this is how I can rewrite this expression, right? Is it not? So once we get this expression, what is going to happen, right? So if we differentiate with respect to ay by g, we can immediately see that the left-hand side will become 0 because delta is a constant. So then we will get L times the derivative of 1 by r with respect to ay by g. So what am I doing? I'm differentiating both sides with respect to ay by g. Ay by g is our variable. Then I will get kv, right? So because kv times ay by g, if I take the derivative with respect to ay by g, I will get kv, right? So consequently, what will happen is that the derivative of 1 by r, which is the curvature, with respect to ay by g, okay, which is the lateral acceleration, is going to be equal to minus L by R. Sorry, not minus L by minus KV by R. So once again, we can see that when we do a constant steering angle test, and let us say we figure out the curvature, the radius of turn, reciprocal of the radius of the turn, and then like plot it against the lateral acceleration, what we get is that like we can figure out the understeer gradient at the state of steering, right? So through the slope. So now it is just the opposite trend, right? So if the slope is negative, then the vehicle is in a state of understeer. If the slope is positive, the vehicle is in a state of oversteer, right? So because we can see that there is a minus sign here, right? So I think that will be what to say. That will be the implication. All right. So I hope that is clear. So we can observe that, like based on different tests, right? So we are essentially getting different outcomes. And one could essentially use a combination of these tests to, in real life, to get idea about the state of steer of a vehicle. But please note, all these are valid only for what to say, a steady state maneuver. Okay, so Vx should be constant, R also should be a constant. Okay, so we have to keep that in mind. Only when the vehicle reaches the steady state, we can take measurements and use these equations. Okay, so we have to be aware of them. Okay. So any questions before we go to the next topic? So I'm going to start the next topic with a question. Okay, so we are going to answer this question through the next topic. Okay, which is a very, very important. In fact, like subjective evaluation of handling performance is is a very challenging area, right? So, companies may use expert drivers to essentially drive their vehicles and sort of like rate the handling performance of the vehicle, right? Amongst other parameters. But the question is, we are all engineers, right? We are all designers. So the question is, at the vehicle design stage, can we do some analysis to get some objective metrics, right? To evaluate handling performance. So in that regard, we are going to ask the question whether, if and how, the dynamic bicycle model okay, can be used for handling evaluation. Okay, how do we use this? How do we do this? Okay, so that is the question we are going to ask ourselves. Okay, so the question that we want to ask is that like if somebody wants to do this evaluation, okay, of handling performance in an objective manner. So we are essentially going to figure out. We are going to learn one technique which can be used. Okay, so we are going to study what is called as the Monroe block. So what I'm just giving you the reference. Please do go and read this. And now we will also see why this impulse test becomes very important. Okay, so if you remember, see now you can see all the concepts that we studied in dynamic systems coming into play, right? So here is where we do a pulse steer test where we give an impulse input and measure parameters and try to come up with quantitative results. Okay, So this paper is titled 4-parameter evaluation method of lateral transient response. Okay, so that's the title of the paper. So go through this paper. And so when was this published? So this is by authors are P. Numero et al. Okay. And this is an essay paper. Paper identifier, the paper number ID is IN074. It's published in the year 1990. Okay, so please do download this paper and go through this manuscript. I'm just going to essentially sort of tell you what the concept is and some of the derivations, which are going to be long-winded. I'm going to leave it to you as an exercise for you. Okay, so please do do. Okay, so as the name suggests, we essentially are going to evaluate the cornering response based on 4 parameters. Four out of these 4 parameters, 3 parameters come from the yaw velocity response. Okay, so 3 parameters come from the yaw velocity response. Okay. And one parameter comes from the lateral acceleration. So, see, when we do this exercise, you will also sort of understand once again why we spend quite a bit of time on dynamic systems theory, right? So, I'm sure as we keep on discussing vehicle dynamics, you will see that many of the concepts that we studied initially in the first module, right, are being put to use. Okay, so what is this? So there are 4 parameters. I will define what those parameters are and also tell you how to get them. So essentially, I will give a so. But what are these parameters? Okay. So now, what is this yaw velocity response? So if we consider the linear bicycle model, right? So you remember, we rewrote the bicycle model in terms of the yaw rate and the side slip angle. So let me show you what those equations are. Right? So let me go back and look at this. So if you recall these 2 equations, right? And then we put it in the state space form, Ax dot equals Ax plus Bu, right? I hope all of us recall these equations. So now we are going to utilize these equations. Okay. So recall the state space representation. Recall the state space representation of the linear dynamic bicycle model in terms of the side slip angle beta t and the yaw rate r of t. Okay, so we had obtained this equation. So I'm just putting it in a concise form. So x dot was axt plus but. We got expressions for these, right? So so we already know this. And where the state vector was the side slip angle beta t, and the yaw rate was yaw rate r of t, or the second state variable, and u of t was delta of t, right? So that's the state equation. So once again, we had already derived this. Okay, so we are going to use this. So let me go back to that equation and point it out to you. So we have already derived this equation. is this equation, okay, that we see now. So we can observe that we had written the state equation where beta and R were the state variables. We have got the A matrix and the B vector, right? So that's something which we have already derived. So let's compare. Okay, so we are going to utilize this to get the corresponding responses. So what are the corresponding responses? Let the output vector, the first output vector that we see, let it be the column vector 0 and 1. Okay, if C is 0 and 1, the output y of t is going to be equal to C1 dot x of t. So see what is meant by yaw velocity response. You know, the input is delta t and the output is r of t. Okay, so we are essentially extracting the yaw velocity, yaw rate, right? So 0, 1 dot beta t and r of t. Okay, and what will we naturally get? We will get r of t. Okay, so how did we get this expression? Because see, when we want to study the yaw velocity response, okay, see, first we want to look at the yaw velocity response, right? So if I want to look at the yaw velocity response, okay, so let me write it here. So we are essentially now looking at the yaw velocity response. Okay, so we can immediately see that if we choose the output vectors, let's say we call it a C1, there is a reason why I'm calling it a C1, right? So because depending on the value of the output vector, we will extract different quantities. So essentially what happens is that, like, if delta of t is my input, okay, the steering angle is the input, and this is our system, right, or the model, system model. So what we get is that, like, we get r of t as a output, right? So then we are talking about the yaw velocity response. And when I take C1 to be 0, 1, I will get r of t as the, what to say. Okay, so the transfer function now corresponding to the yaw velocity response is given by, how do we get this? We essentially use C dot Si minus A inverse B plus D, right? So that's what we are going to do. So it's going to be, let me put it as P1 of S, okay? P1 of S is going to be R of S divided by delta of S, and that's going to be equal to C1 Si minus A inverse, sorry, C1 dot, right? So, okay, C1 dot Si minus A inverse B plus D. Of course, D is 0 here. Okay. So this I leave it as an exercise to do. And if we do this, I'm just going to give you the answer so that, like, all of us know what the answer is. Okay. So you get this as the answer. Okay. I just give you the answer so that, like, you can check this. But then, like, I leave it here as an exercise. Okay. So please do this as an exercise once for understanding. So substitute all the values for A, B, C1 and so on. Okay. Show that P1 of S, which is going to be equal to R of S by delta of X, is this. Okay. So that's, I leave it to you as an exercise. Okay, so you don't need to submit it as a homework, but this is just for your own benefit. Okay, so it's a long-minded derivation. Okay, so but then I have given you the answer. All right, so please do. Okay, yeah. Okay, okay, so but most importantly, we want to figure out what do we extract out of it. Okay, so we are going to extract 3 parameters from this transfer function. Okay, so we evaluate the following 3 parameters or metrics from P1 of S. What are these metrics? Okay, the first one is the steady state gain. Okay, what is this steady state gain? Okay, the steady state gain is denoted by A1, okay, of the yaw velocity response. As we know, it is the value as t tends to as v as s tends to 0, the value which the transfer function takes. Okay, so this is the definition of the steady state gain, which we recall. So essentially, we are essentially studying the impulse response, right? So that's what we are doing, and we want to figure out what is the steady state gain of this yaw velocity response. So now, if we substitute s equals 0, that is, if we take the limit s equals 0 of this transfer function and simplify this, so what we will be getting is the following. Okay, so once again, these simplifications, the algebra, I leave it to you as an exercise, but it's very simple, right? So when we substitute s equals 0, or when we take the limit s equals 0, we are only going to be left with the constant terms in the numerator and the denominator, which when simplified is going to get us this formula, okay, for A1. All right, so that is the first what to say expression. So once again, what is this thing? So it is this constant, okay, in the numerator divided by this constant in the denominator. Okay, so those are the two constants that we are looking at. Okay, so that is the steady state thing. So the next parameter that we quantitative metric that we look at from the yaw velocity response is the natural frequency of the yaw velocity response. Okay, so how do I evaluate the natural frequency of the yaw velocity response? So once again, from the transfer function, right? So this, let's say we call it as Fn, that is going to be equal to omega n, which is the corresponding angular frequency by 2 pi. Okay, Fn is going to be in hertz, omega n is going to be in radians per second. Now, how do we get this? We are going to evaluate the denominator. You remember the second order system that we studied? The denominator of the standard second order system is going to be of the form s squared plus 2 zeta omega n s plus omega n squared, right? So we can immediately see that the term which is here is the square of the natural frequency in radians per second. So we can immediately see that omega n is going to be equal to the square root of, so first let me write down the term. It's going to be 4 C alpha F C alpha R L times L plus KV Vx squared by G, okay, divided by M Vx squared by Z, okay, the whole thing squared. Okay, so I hope it is clear how we got this, right? So because we just compare the denominator polynomial with the standard denominator polynomial of the second order underdamped transfer function systems and transfer function. The denominator polynomial is s squared plus 2 zeta omega n s plus omega squared. So that's how we compare and get this, okay, for omega. And the third parameter is the damping ratio of the natural frequency. How do we get the damping ratio? We look at this term, okay, the constant term. Sorry, not the constant term, coefficient of S, right? If you look at the coefficient of S, we equate it to 2 zeta omega n, and then like we essentially get this, right? So the third quantity is going to be the damping ratio. Okay, damping ratio zeta. And how do we get the damping ratio zeta? We essentially equate 2 zeta omega n with 2 C alpha F plus 2 C alpha R divided by MBX plus 2 C alpha F LF square plus 2 C alpha R R square divided by Iz X. Okay, so this is what we have. Okay, so if we essentially process this and substitute for omega n, we essentially will get the values. Okay, so pretty straightforward. Okay, so these are the three parameters that we get from the yaw velocity response. So if I were to write the exact expression for zeta, it will be this. Let me just include the final answer so that like you can double check. Okay, so as I told, please do all these as exercises, but very simple algebra. Okay, it may involve some time, but I'm sure you can figure it out. Okay, so this is going to be the value of z. Okay, so this is from the yaw velocity response. Then we look at the lateral acceleration response. So in the Memro plot, the fourth parameter, these are three parameters from the yaw velocity response. The fourth parameter is from the lateral acceleration response. So how do we essentially get the lateral acceleration response? So once again, we visualize the same model as our system. Okay, and the input is anyway delta t, and the output is the lateral acceleration, AYT. We recall what was the expression for AYT. Now we are not dealing with steady state. Please note, we have to go through the transient model. So that is why now you can understand why I spent quite a bit of time in recapping dynamics and getting the general model equations, right? That will apply under dynamic scenarios, right? For our consideration. So AYT, if we recall, it was y double dot t plus Vx times psi dot of t. We recall from our at the beginning when we did the derivation for the linear bicycle. So this can be written, as we know, this can be written as Vx times beta dot of t plus Vx times r of t. Okay, so this is also something which we have already done, right? So we know from the definition of beta and r what this is. Okay, so now if I take the Laplace transform on both sides, I will get and with zero initial conditions, Ays will be equal to s times Vx beta s plus x r. Did I get this? Take Laplace transform with zero initial conditions, because we are looking at the transfer function, right? So okay, and apply zero initial conditions. So once we do this, we get this expression, right? So now we get the lateral transfer function for the lateral acceleration response. So I hope things become clear now, right? So why we are essentially going to do this. So this becomes s times Vx beta of s divided by delta s plus Vx times r of s divided by delta s. Okay, so this is the transfer function we are after, but this is what we get. Okay, now please note, this is something which we just derived. Whatever I'm indicating in parenthesis is P1 of s. We just derived it. Okay, now we need to derive this P2 of s. How do I do that? We follow a similar method. Okay, we essentially use the state space representation, but with a new output vector C2 dot Si minus A inverse B plus D, where C2 is now 1, 0. Okay, why 1, 0? Because if I take the dot product of C2 and X, okay, which is 1, 0 dotted with beta and R, I will get beta. That's exactly what we want here, right? We want beta to come in the numerator, right? Sorry. Okay. So of course I'm suppressing time here, okay, in this formula, but you get the idea, right? Why we choose C2 to be 1 and 0. So once again, a very long-winded derivation. I'm not going to essentially ask you to do this, but if one does it, what will happen is that ultimately the lateral response transfer acceleration response transfer function comes out to be a numerator polynomial divided by a denominator polynomial. once again, this is an optional exercise. Please do it if you want to learn the complete thing. But then this is what will happen. Okay, so it's going to be a little bit long-winded. Okay, and that will give us our fourth parameter. So what is this fourth parameter? The fourth parameter is going to be the following. The fourth parameter is going to be the phase delay at 1 Hertz. Phase delay, which is delay denoted by 5 at a frequency of 1 Hertz. So this is how Mimaro and co-authors define these parameters. They essentially calculated at a frequency of 1 Hertz and quantified it. Okay. So how do we calculate this? Like we know frequency response, right? We essentially get P of j omega. So in this case, it will be the phase of n of j omega minus the phase of d of j omega, right? And this should be evaluated at omega equals 2 pi radians per second. Please note, 2 pi radians per second corresponds to a frequency of 1 Hertz, right? So omega equals 2 pi f, right? So that's what we are using. Okay, here. So please note that omega, we need to evaluate it. Omega equals 2 pi radians per second. Okay, so this is something which once again I leave it as an exercise, but I'll give you the final expression. It will come to be the following. Okay, so this expression will come as this. Okay, finally, we can get 5 to be this. Okay, so once again, this I leave it to you as an exercise for you to do. So what we have done is that like we have essentially used the linear dynamic bicycle model along with all the dynamic systems theory that we did to get the corresponding response functions, right? What do I mean by response functions? The response function essentially means essentially the lateral acceleration response function and the yaw rate response function, right? So, and once we get these response functions, we evaluate these 4 parameters, and then we generate what is called as a Mimaro plot. Okay, so these are the 4 parameters which come into play, and then like we essentially plot the Mimaro plot. So let me explain what this Mimaro plot is. So we give a pulse steering input, and then like measure variables in practice, and then like we essentially are going to plot Mimaro plot. It's on 2 dimensions, but then there are going to be 4 axes. Okay, so this is not like a 2-axis plot, but then a 4-axis plot. Okay, so what do I mean by that? Okay, so it will have axis. Okay, and what we plot is that like we plot Fn in hertz along this axis. Okay, 5 in degrees along this axis. Okay, but becoming less negative. Okay, as we go towards the right, and zeta, the damping ratio along this axis, and the parameter A1, which is the steady state gain along this axis. Okay, so that's what. So now let's say like we calculate these values, right? So what we do is that like we plot them. Okay, so suppose let's say for some operating condition A1 value is here, right, and F1 value is here, and zeta phi value is here, zeta value is here. So what we do is that we mark all these 4 points on the 4 axis, and then this join. Okay. Okay, so we just join them to form this quadrilateral. Okay, so essentially we have the shape, all right, and we have this rhombus shape, okay, which is a graphical representation of these parameters. And of course, we will have different families of these curves for different speeds. Okay, so please note that all these parameters have speed coming into play. Okay, you can see that Vx is in the expression. So even if all other parameters are held constant, this is parameterized with respect to speed. Okay, I'm going to give you an exercise where we will essentially deal with the speed, what to say, speeds. Okay, so we will see that, like as speeds vary, we essentially are going to have better, we are going to have a family of memoroplots. Okay, so but there is a physical interpretation of these four parameters, right? What is the physical interpretation? So if the value of A1, okay, tends to the left, that means it increases in magnitude. Essentially, we are going to have better heading easiness. So what do I mean by heading easiness? Because A1 is a steady state gain, right, of the lateral, of the yaw rate response, right? So it's yaw rate divided by the steering input at steady state, right? So now, if I essentially have a higher value of the steady state gain, right, then like for the same steering input, I will get a bigger yaw rate, right? So, or in essentially to take the same turn, right, at a certain rate, I can do it more easily because I need to give a smaller steering angle, right? So that's why it's representative of heading easiness. Okay, if the value of Fn increases, okay, if the value of Fn tends upwards, that means that heading responsiveness would be better. As we know, higher the natural frequency, faster will be the response, right? In terms of rise time, settling time, and so on, right? So that is why if we are essentially going up along this curve, along the F1 axis, we are going to respond faster. If the value of zeta goes down, okay, that means that zeta is increasing. Okay, so graphically it's going down, but that means that zeta is increasing. So higher directional damping, which is also good. That means that my oscillations will be dampened out, right? So when I'm taking a turn, so it will result in higher directional damping. And the value of phi tending to the right, that means that smaller lag, okay, or smaller phase delay, okay, or phase lag. I don't call it phase delay, phase lag. That means that improve following controllability. Why? Because if I want to track a curve, my delay or the lag in the lateral acceleration response will be smaller. So I can essentially have better following controllability if I go to that. Okay, so these are the physical connotations associated with the Memro plot. And if you want the best possible vehicle, we want to ensure that the Memro plot expands in all the directions. Okay, so that's what we want. All right. So, but as with all other things, like not so straightforward, right? So why? Because we essentially, if we want to adjust some parameter here, there is always a trade-off in another parameter or the other set of parameters. Okay, so higher the area of the Memro plot, better it is. Then in reality, there are always going to be trade-offs. Okay, so this brings me to homework number 7. Where I am going to give you some vehicle data. So, and then I will tell you what to do. Okay, so let me first give you the vehicle data. So, this is the vehicle data that I am giving you for 7. So, the first problem is that, like, given this data, find a KV for all the KV for all the cases, and then comment on whether they are oversteered, neutral steered, and or understeered. Okay, so state your observations. Okay, based on these calculations, you can do that. Okay, and then the second one is the following. Okay, second one is the following. So consider a range of Vx from 60 kilometers per hour in steps of 10 kilometers per hour up to a speed of 150 kilometers per hour. Okay, plot the Mimaro plot for the three vehicles and comment. Okay, so I hope I have given you all the data which will be required to plot the Mimaro plot, because you have W, L, LF, LR you can calculate, H, I, Z, C, alpha, F. Oh, this should be C alpha R. Sorry about that. So this should be C alpha R, okay, not C alpha F. And then this is a rolling resistance coefficient. You don't need this at this stage, so forget the last row, but then you need till the corner input, okay? So you can see that you can calculate all these parameters for these class of vehicles, but then you need to write a code, right? So that you consider values of Vx from 60 kilometers per hour to 150 kilometers per hour, plot the Mimaro plot for all the three vehicles as a function of speed. So for each speed, you will get one curve, right? So for each vehicle, that you will have three Mimaro plots, okay, one for each vehicle. For each vehicle, you will have a family of curves, okay, corresponding to the range of speeds under consideration. Okay, so that's what I want to see. All right, so please plot it and then comment, okay, on what you observe, and also related to the transient response characterization that we studied, right? So initially, okay, and then try to correlate and make some observations. Fine. Okay. So that is the Mimaro plot, and this is the homework which I want to assign to you through this class. Okay. So this concludes our discussion on lateral dynamics. Are there any questions before we close today's lecture?
Sir, in your velocity response, why we have taken d term as 0?
So because the direct transmission term is 0 in this model, right? So because you look at the model itself, right? So n is essentially greater than m. So that is the reason why we have. You see, we don't have delta dot coming into play, right? So that's why we can ds.
Sir, moreover, this bicycle model, they are not CISO systems, right, sir? They are single input and multiple outputs.
Multiple output, but then we are essentially analyzing one output at a time. Okay, so that's the approximation we have, right? So
okay.
It is viewed in that perspective.
Okay,
see, of course, if you want to analyze all the outputs at the same time, you will have an output vector, right, rather than a scalar output. We are just using this perspective, so that we can apply the tools that we have got.
Okay, sir. So in this case, yt is equal to c vector and dot x vector. So x vector, c vector can be it can be written as a 1 1 in case of a multiple output, right, sir?
So 1 1 means you are essentially taking beta and r. So if you want to capture both the outputs, what you should do is that if you want both beta and r as outputs, what you should do is that you should take the identity matrix. Yeah, right. Not the column. Okay, so C will become a matrix. I hope that clarifies, right? So,
yes, sir. Thanks.
But I'm just going to erase this so that it doesn't confuse when you read the notes in isolation, right? I hope that's okay.
Yes, sir.
It will be there in the video, but not in the notes. All right. Any other questions? No. Okay. So if not, let me stop recording.